Hello everyone, this is Anil. In this video, we are going to discuss about transfer function derivation. In the previous video, I have already explained about convolution integral and impulse response. In this video, we'll focus on how to derive transfer function. In convolution integral, we represented input in this way. We represented input in this way, integral minus infinity to infinity u in tau delta t minus tau d tau. And this is one of the definition of impulse. This delta int is known as unit impulse signal. And this is one of the definition, delta int is 0 for all t not equal to 0 and integral minus into infinity delta tau delta tau equal to 1. Okay, these things I have already included in last class. And for this delta int, the response is known as h int and it is known as impulse response. And for this input unt, the response y int, okay, integral minus infinity to infinity u in tau h t minus tau d tau. So this is known as convolution integral. Okay, the detailed derivation of this I already included in last video. The same thing I can also write in this way, u in t convolution h in t. So coming to this video, in this video we'll focus on derivation of transfer function. So for this derivation we need Laplace transform definition. So the definition of Laplace transform is we apply Laplace on time domain signal x in t. So what will happen when you apply Laplace is the signal will get multiplied with exponential minus st dt under integral minus infinity to infinity. And in S domain we apply Laplace inverse. Then the definition is that x in S will get multiplied with exponential st ds, and the integral varies from sigma minus j infinity to sigma plus j infinity, and we have additional this term 1 over 2 pi n j. So we start from this convolution integral y in t. Okay, this is y in t. On this y in t we apply Laplace transform. Okay, when you apply Laplace, the signal y in t gets multiplied with exponential minus st dt and it varies from minus infinity to infinity. Okay, now what we do is this y in t, this is the definition of y in t. The same thing we include here. Okay, once we include here, now we interchange the order of integration. This tau integral we take it outside, this t integral we take it inside. Okay, we swap the integrals. So when we take t inside, we include in bracket the terms with respect to t. So this is the term with respect to t, the thing I have included here, and exponential minus st dt, the thing I have included here. The remaining terms, so the remaining terms are u tau that I included here and d tau, that term I have included here. Okay, the next thing is we take this t minus tau with eta. Okay, then what will happen, h eta and exponential minus is t will be eta plus tau, that thing I have included here, and dt means then it will become d tau. Okay, outside it doesn't change, d tau. Okay, input u in tau, input u in tau. Now I separated this with respect to okay, with respect to integration. So here we have u in tau, exponential minus s tau, that thing I have included here, and d tau. Okay, and here we have h eta, the same h eta, and we have exponential minus s eta, exponential minus s eta, and d eta and d eta. Okay, this is again standard definition of Laplace. Okay, thus the input get multiplied with e to minus s tau d tau. Here h with getting multiplied with, this is the standard definition of Laplace transform. Okay, the final result will be this y in s. Okay, this y in s equal to, this is your u in s and this is your h in s. So what we have done here is that the convolution integral is, to get the response y in t, we have to solve this complex integral. That thing we reduce to simple multiplication. Okay, y in s equal to u in s into h in s. So this h in s is known as transfer function. For transfer function definition, so there are two definitions. One of the definition is Laplace of h in t. This h in t is known as impulse response. Okay, let me go to next slide. And the other definition is that for seesaw case, h in s. Okay, h in s written as y over u. Okay, y in s over u in s. So this thing we already discussed in last class. So y in t will be u in t convolution h in t. In Laplace domain it will be product form. Okay, here h in t is known as impulse response. Here h in s is known as transfer function. And for transfer function there are two definition. One of the definition is with respect to this. Okay, ratio of Laplace transform of output of the system to its input. The second is with respect to impulse response. Okay, Laplace transform of unit impulse response of the system. So you can pause the video and you can clearly read this standard definition. So this is the definition taken from book, standard books. And if you take here input u in s equal to delta in t. Okay, the Laplace of delta in t is 1. So in that case, y in s equal to h in s. So these are some applications in block diagram reduction technique. So these are the things I already derived last class. So I am directly going to results. So what will happen? When two blocks are in cascade form, then it will be h2 times h1. When in feedback form, this is how we get it. Okay, h1 divided by 1 minus, already we have minus, and what we have in numerator, what we have in forward path h1, and what we have in feedback path h2. Okay, the same thing I have written here. So in this video, basically I want to include the derivation of transfer function and what is transfer function definition and some of the applications. Thanks for joining. Thank you.